Last time we saw the very important concept of reflection of pulses from a boundary, and to that end we explored in detail reflection of a single pulse from a rigid boundary, and we saw how the reflection results in phase inversion of the reflected pulse, and how also it initially results in potential energy converting to kinetic, and then again kinetic converting to potential. So we were looking at reflection of a transverse pulse or wave at a boundary point. So what we saw, the first part of this was we have a situation like this, a transverse pulse traveling like this along a string, and there's what we call a rigid boundary over here. And we saw that what happens is as this pulse reaches here, it gradually changes shape from this to this, then this, and then eventually becomes flat for an instant. And then the reflected pulse starts coming back. So first it's like this, then like this, then eventually you have the complete reflected pulse, the inversion of the first pulse, so having the same width and the same height or amplitude or whatever as the original pulse. Now we also saw that during this process, how the shape changes, and apart from that, also we saw about how the energy changes. So we saw that, for example, your pulse is traveling like this. So right now it's a combination of potential energy in this region and this region, the elastic potential energy. And also there is, these particles are tending to move up, these particles are tending to move down. So there's kinetic energy also. So the total energy of the pulse is a combination of kinetic energy plus some kind of potential energy. And this energy is shifting. But as this reaches this kind of a situation, it becomes like this, you can see that the amount of potential energy starts to decrease, because this becomes less compared to the amount of stretch here and here. But on the other hand, these particles are all now rapidly coming down. So going in this direction, kinetic energy is increasing of the pulse and potential energy is decreasing. So we saw you reach a situation where momentarily what happens is that the string becomes completely flat. Like this. So at this point of time, there is no potential energy. Just at that instant, these particles are all coming down very fast. Like this. So it is pure kinetic energy at the instant when y is equal to 0 for all points on the string. So this is the case where your potential energy has become 0. So all the kinetic energy is converted to potential energy. And then as the pulse reflects in phase, so वापस ऐसा हो जाता है, like this first, and then eventually like this. So again, now it's a distribution of kinetic plus potential. There's kinetic energy now. These are going up and these are coming down. So again, it becomes the combination of kinetic energy plus potential. So overall, what happens is energy of the pulse remains conserved. But during the reflection, with phase inversion, first potential energy converts to kinetic energy, and then again kinetic energy reconverts to potential energy, such that the final energy is equal to the initial energy, which is equal to the sum of the kinetic energy plus potential energy. But in between, the energy is equal to the maximum kinetic energy, which is equal to initial or final energy. At that point of time, the potential energy becomes. Okay, so this is what we understood about the energetics, or how the energy propagation happens while the phase inversion is happening. And of course, we discussed in detail how to understand the shape changing by looking at it as a superposition of forward pulse like this and an inverted reverse pulse like this. And we saw that the superposition of these two is just a resultant shape which is changing with time. Or something like this. And that's how we saw that the shape is continuously changing. We discussed all this in detail last time. So you can go to that. Now today we'll also discuss about the reflection at a soft boundary or a flexible boundary, where is the opposite of that. There is no phase inversion. Instead, the amplitude doubles momentarily. And therefore, initially what happens is, as the pulse is reflecting, initially your kinetic energy is converting to potential energy. And then again, potential reconverts to kinetic and total energy remains conserved. So this is a quick recap of the last couple of things we saw. So you have all this in your notes, don't need to write down, just to do continuity with last time lecture. All right, now moving on to the situation of reflection of a transverse pulse. At what we call a soft or flexible boundary. So we'll see that the physical situation of a soft or flexible boundary is something like this. If we have, let's say, a vertical pole over here, it says that it's kind of frictionless. It's a smooth kind of fixed pole. And we have long string which is at the end attached to a ring like this. This is a ring that can slip freely on the pole. And this is a stretched spring, tension T, linear mass density U like this. And what is happening is, from this end, somebody has created a pulse which is traveling along this direction, speed V, and it has an amplitude A and a width W. And so what will happen here is, at the boundary, that is the ring, there is no resistive force. There is no resistance force or resistive force to transverse displacement. And hence it is completely flexible to transverse displacement. So there is maximum transverse displacement. It's the opposite situation of the fixed boundary that is. So to understand how the shape changes, what we do here is we model it with something where energy would remain conserved, but in such a way that there is maximum displacement at this point. So when we do that, we see that initially something like this happens. But eventually, at this point of time, the peak is still coming closer. But eventually, something like this also happens, where this now becomes more than E. Peak still by 2. And from there on, what happens is that it again starts going in this direction. Eventually, going back to this, and further eventually. Going back to this, where so in this series of events, what is happening is as you're going from this state to this state, you can see that your kinetic energy is decreasing and your potential energy is increasing because the string is more and more bent. And when you reach this state in between, all points on the thread are at the maximum displacement. So particle velocity is 0. So kinetic energy is 0. Potential energy is maximum. And then as you go from this state to the lower states, coming back to the normal shape, but the peak traveling in the opposite direction, again potential energy converts to kinetic energy. Potential energy starts decreasing and kinetic energy starts increasing. Till here, it is again the same balance of kinetic and potential as the initial state. So this is about the energy relation. Just make a quick run through of this. Then we'll also discuss about how the shape is changing. How we can model that shape change by considering superposition with a wave in the same phase but traveling in the opposite direction. Okay, so let us look at next aspect of this. Understanding the shape of the changing pulse. We take one situation where you have the actual thing, which is this pulse, which is hitting this flexible kind of boundary. And you model this as a situation where you look at it like the superposition of two pulses of same phase and same shape and size, but traveling in opposite directions. You get an identical pulse, not like a mirror image, but traveling in the opposite direction. And their midpoint right now is this point, which is the equivalent of this point over here. So after some time, let's say they are superimposing like this over here, that this pulse would be something like this. This pulse would be something like this. So this superposition will become now something like this. Just give me a second here. Yeah, so the superposition of this thing would look like this. Because you can see it's the sum of two positive quantities. It would become something like this at the point. So correspondingly, here you can see how the wave shape is looking. Just one side of that, but this amplitude is still the same. In the next image, you can see that if we have a situation where there's slightly more amount of overlap, not full overlap yet, but comparatively more amount of overlap. Now you can see the peak is also getting affected. But the displacement of this one starts from somewhere in here. You can see that the resultant will now look something like this. So this has become E plus delta, one more than the individual amplitudes. So correspondingly here, you can see that shape has now become such that this this was still E. The field is still shifting in this direction. And then there is the complete overlap. When the complete overlap situation happens, you will see that it will have to double. It will have to become like this. The resultant will have to be 2A. It will have to be W by 2 1. So the corresponding shape here is shifted to this. And then you can see it further proceeds back. So this is the method you can use by comparing this situation, the half space in this situation with the half space in a situation where this is superposition with a pulse, with we can say an identical pulse in same phase, but traveling in opposite direction. So there what happens is as they superimpose, the symmetry point O is forced to have maximum possible displacement. So the flexible boundary's nature is also the same. That point where the flexible boundary is present, that is forced to have maximum possible displacement. So that is why this situation, the reflection from a soft boundary, has a similarity in terms of shape on half the side as this situation. Okay, so just make sure that you understand these diagrams, then we'll look at a similar numerical type of example also. All right, so this is clear. So let's do a quick numerical type of problem based on this. So again, I have this imaginary triangular kind of pulse. So why I'm saying imaginary is because, as you know, in real life, no actual pulse on a string can have this kind of a shape, because it cannot have sharp corners like a triangle has. The corners have to be smoothened like the curved kind of pulses that we have. That's why I'm saying there's an imaginary kind of pulse, not an actual pulse. So we have this imaginary triangular pulse, which is, let us say, this height is 4 centimeters and this width is 6 centimeters, something like this. And it's traveling in this direction with a speed of 10 centimeters per second. And now there is a flexible boundary over here. The shape of a pole over here. Okay. So also this end is at a distance of, let's say, 20 centimeters. So this is that ring that slips smoothly on the pole. So to find, first of all, the displacement of the ring, vertical displacement, at t equal to 2.1 seconds, t equal to 2.2 seconds, 2.5 seconds. Okay. Find the Y max or peak points displacement at the same times. And also find the maximum displacement of the ring and the time at which this occurs. So just try this out. I will minimize the diagram to show it fully to you. In fact, as you're finding the displacement of the ring, also draw the pulse shape at each of these ends. Last question is the maximum displacement of the ring and at what time the displacement is maximum. Start with question 1 and 2, so that then you can come to the last one. If you start with part 1 and 2, then you can come to the last part, which is the maximum displacement of the ring and at what time that displacement is maximum. Okay, so let's see the answers of each of these parts. At this point of time, the displacement of the ring should be equal to 1.33 centimeters upwards, or 4 by 3 centimeters upwards. At this point of time, the displacement of the ring should be 2.67 centimeters, or 8 by 3 centimeters upwards. And at this point of time, it should be back to 1.33 centimeters upwards. Now let's see why that is happening. So if you go by the superposition method, this is where your forward pulse is at t equal to 2.1 seconds, then it should be 1 centimeter beyond the symmetry point. This should be 1 centimeter beyond the symmetry point. So your reverse pulse, I mean the superposing pulse of same phase, that should be here. So yes, one traveling in this direction. This one traveling in this direction. This, 1 centimeter. So you will see that the resultant displacement at this point is, sorry, it is double of that. So minus it will be 2.67. It will be double of this. And this will be double of this. There can be double of this. This will be 8 by 3, this will be 16 by 3. Anyway, so the superposed effect of these two adding up, the resultant effect of the summation of these two will now look like this. Now let's see the addition of these two. That will become flat like this. So if you want to understand the mathematics of this, you can see that at this point of time, the forward pulse at the point where the boundary is located, or where the ring is located, if you want to understand that at this particular point, how much this displacement is. So, you see that because this is 1 centimeter, which is 1/3 of this total. This 1 centimeter is 1/3 of this total 3 centimeter. So you see that this height over here is suppose some y. So that will become 1/3 of this, which is 4 centimeters. So y by 4 should be equal to 1 by 3. So that y should be equal to 4 by 3 centimeters. So now that's why over here the y net, which is the displacement of y because of the first pulse, that is this one, plus because of the second pulse, which is the reverse one coming in that direction. So each of them are giving a displacement of y by 2 and 4 by 3 and 4 by 3. It is 8 by 3, approximately 2.67. That is the displacement of the point where the beam is present. This point. Is this clear? And also the shape of the medium at this instant will now therefore look like this. The actual medium will look like this. Where this peak. But instead of this, like this. Okay, this should be clear. We will be present here. What the shape of this will look like. So this would be 2 centimeters. This would be 3 centimeters. So the peak point will be at an amplitude of 4 centimeters. So this is at the instant t equal to 2.1 seconds, which we are getting by this superposition method. So the mathematics is a bit complex, but again, just keeping in mind the symmetry and similar triangles and things like that, you can understand how the superposition is resulting in this. Okay, now similarly try it out yourself for 2.2 seconds. You'll see that the overlap is now over a span of 4 centimeters when 2.2 seconds happens. So, you know, the blue colored forward pulse has gone 1 centimeter further, and this one has come 1 centimeter further back, the red one. So the overlap, instead of being over a span of 2 centimeters from here to here, then the overlap will become 4 centimeters in span. So all of you people are following this. You will see that the boundary point or that symmetry point is now here. This is the point. A little more careful while doing the diagram. This point is here. Right. So this has gone 1 centimeter ahead, as you can see. So this has gone 2 centimeters ahead. So likewise, the other one has come here. So that's where this peak point is. So this has come 2 centimeters behind this. So the span is 4 centimeters of the overlap. So now if you look at how the superposition will act. Between this point and this point. This. So again, if you see this height, to the right, this is h. This height is going to be, again, from similar triangles, you will see it is 2/3 of 4 centimeters. Because this total height is 4 centimeters. Remember, this is 4 centimeters. From the combination of these similar triangles, understand, this is 2 centimeters, this is 3 centimeters. But now let's look at the overlap. So how will the overlap be looking like? the overlap of these pulses will look like this over here up to this here. Now beyond this, see, initially this and this are adding up to this point. So they are adding in such a way that this point's displacement is becoming something like this. Something like this over here. Probably more something like this. Because it will become 2h. And then up to this point, the sum of this thing coming down and this one going up will be constant. So as I told you, these graphs and shapes are a bit tricky to work out. So this is what the superposition will result in. This kind of. Where you now realize that this peak will have to be double of this. So at this point, these two are superimposing. So they are in 2h. That's why the ring's displacement when we draw it, that will be this is 8 by 3 centimeters. So this will become 16 by 3. So this is how the shape of the medium is looking like at 2.2 seconds. If we are going by the superposition of the pulses. Now actually what is happening, it's not this. Actually it is the displacement of the ring. So when we draw the actual medium shape, that will be something like this one. Okay, so that's what this thing will look like. And get some more accuracy into this. So there's a subtle shift in slope. like this. And now this is where the ring is present. Anyway, something like this. So the displacement of the ring, you can see, would have become like this. It would have become 16 by 3, or like this. And this width would have become should be 4 centimeters. Again, there is a correction here. The ring should be here. Get this kind of picture. This is where the pole is. Right. So I have done with this now. Right. So this is the position of the medium at 2.2 seconds. So from this shape, it goes to this. And at 2.3 seconds, you will see that they will perfectly overlap. And it will become that half triangle, that right angle half triangle with a peak value of 8 centimeters. Right. So next, if you look at, you are not given in the question directly, but given an indirect question that when is the rings displacement maximum? So that you'll see will occur at 2.3 seconds. At that point of time, the shape of the medium will now look like this. So you can see that the ring would have gone through a displacement now, which is 8 centimeters. And the width of the pulse would reduce to 3 centimeters. At this point of time, the boundary is present here. That's a pole. This will give you the answer for the last part of the question. So that at what point of time the ring's displacement is maximum, and what is that maximum displacement? This is the maximum displacement for the ring. But at this instant, the overlap picture, they are perfectly overlapped. The overlap picture is what is happening. These two are merged on each other. The resultant displacement is a triangle of the same width but double the height. This is when their peaks coincide. So this is the instant when the kinetic energy of the system will be zero, and the potential energy, the elastic potential of the energy of the string will be maximum and equal to the total energy. Maximum stretch, but all the particles have reached maximum displacement. So momentarily they are at rest. But del y by del t is zero because y has reached its maximum. Okay. So from here at 2.4 seconds, it will be back to where it was at 2.2 seconds. It will be back to this shape. And then at 2.5 seconds, it will be back to where it was at 2.1 earlier, which is this shape. And then at 2.6 seconds, the pulses left the boundary completely. So 2.4 seconds, same shape as 2.2 seconds, that kind of shape. Then 2.5 seconds, same shape as 2.1 seconds. So this one was like this. The earlier one was more interesting than this also. Change slope than this. that kind of shape. This shape, earlier to that this shape. Okay, so hope this application is fully clear. Okay, so see the progression once again of the wave, how it goes. So from this kind of shape, right, as this point would have gone 1 centimeter beyond the ring, had there been no boundary, the shape changes to this. And as it would have gone 2 centimeters beyond the ring, the shape changes to this. And as it goes 3 centimeters beyond, it changes to this. Then it comes back to this shape, then comes back to this shape, then it comes back to the original shape, but the velocity being in the opposite direction. So that's how the progression of the pulse would look in this case. Now moving on from this to reflection of a continuous wave. So for example, we have an incident wave like this, and on one side of it there is a rigid boundary. Let's say this is at x equal to 0. So if our incident wave has the equation, let's say a naught sine omega t minus kx, because it's traveling along the positive x direction. So our reflected wave, assuming there's no loss of energy, will have same amplitude, same frequency, but opposite direction and some phase constant. Now this phase constant, if phi, that depends on the nature of the boundary. And by nature of the boundary, I mean whether it is rigid or it is flexible. This is what we need to remember. So the reflected wave has the same frequency, omega by 2 pi, as the incident, travels at same speed, v equal to square root t by mu, that is f lambda, or that's the same thing as omega by t. But in opposite direction. And it has a phase constant phi, which depends on whether it is a rigid boundary or a flexible boundary. So the minus sign between omega t minus kx is changed to plus because the direction is reversed. But the rate at which the pulses are coming from the incident wave, that will be the same as the rate at which the pulses are getting reflected from the boundary. So the omega will remain the same. And once omega is the same, k will be the same because they're traveling to the same medium. So v is same. So v being the same, omega by k being same. So like that. Okay. Now, what do we mean by this? So let us understand. In the case of rigid boundary, at x equal to 0, the reflected wave equation at x equal to 0 should have inverted phase compared to the incident wave equation at the boundary x equal to 0. So now you just substitute that. So your incident wave equation was a naught sine omega t minus kx suppose. So y incident at x equal to 0, that is at the boundary position, is e naught sine omega t. Now similarly, your reflected wave equation was e naught sine omega t plus kx plus the phase constant phi. So the reflected wave is creating how much displacement at the boundary position? X equal to 0, x equal to 0 is the boundary position. Is creating a disturbance of a naught sine omega t plus phi. Now in case of rigid boundary, there should be phase inversion. So phase inversion means that the displacement created by the reflected wave should be minus of the displacement created by the incident, because the positive pulse should get reversed, the negative pulse should get reversed like that. Okay? So that means e naught sine omega t plus phi should be equal to minus e naught sine omega t. So that shows you that the phase constant should be phi, or in general you can say 2n minus 1 pi, any odd multiple of pi. But the easy one you get is pi. Okay. Whereas if the same thing is happening in the case of flexible boundary, what will happen at a flexible boundary? Is that the reflected wave should be or should create pulses in same phase at the boundary, which is x equal to 0. So that means y incident at x equal to 0 should be positive of y reflected at x equal to 0 instead of negative. So that will show you that e naught sine omega t should be equal to e naught sine omega t plus phi. So the simplest solution here is that phi should be 0, or in general you can take 2n pi, even multiply that. So this is how we relate the reflected and the reflected wave equation when a sinusoidal wave is incident on some kind of boundary. If a sinusoidal wave is incident on a boundary traveling along the positive x direction, the wave equation is like this. Then the reflected wave will be traveling along the negative x direction. So equation will be like this, but with a phase constant phi. So that phase constant will depend on whether the boundary is rigid or it is flexible. If it is a rigid boundary, then it's according to this going to give a phase constant of pi, because there is phase inversion. If it is a flexible boundary, then it's going to give 0 phase constant, because there is no phase inversion, or 0 is equal to 2n pi. And here remember, the amplitude of the reflected wave is the same as the incident, because we are assuming there is no dissipation of power at the boundary. The power incident by the incident wave is equal to the power reflected by the reflected wave. Okay, so just make a note of this and make sure you remember this concept, okay, because next in numerical problems we'll see how to be applying this. Okay, so that's the concept of the phase constant for the reflected. Now next we come to a very interesting kind of equation where along with reflection there is transmission also happening. So these are the type of questions I've shown you in the worksheet also. Suppose you have a situation where there's a combination of two strings which are attached. But one string is of a different kind of gauge, so considerably heavier than the other string. So now suppose this point x equal to 0 is a boundary or a junction point between two strings. This is group number 2, which has linear mass density, let's say mu2. This is group 1. It's a linear mass density mu1. And what is happening is we have an incident wave like this. So a harmonic wave given by the equation y incident is equal to some amplitude into sine omega t minus kx is propagating along the positive x-axis to group 1 and is incident at the junction x equal to 0 with a heavier group, which is group 2. Now given that mu1 is 1 gram per centimeter, mu2 is 4 gram per centimeter. The combination of ropes has a uniform tension equal to 1000 newtons, and the frequency of the incident wave is 50 hertz. So first thing is find out the wavelengths, frequencies, wave speeds, and omega and q, that is angular wave number and angular frequency for incident wave, reflected wave, and transmitted wave. From that, write equations for the reflected wave and the transmitted wave. And third part, if the amplitude of the incident wave, that is V naught, is let's say 2.4 millimeters, then find the amplitudes, say AR and ET, of the reflected and transmitted waves. And this assume zero dissipation of power or energy because of the boundary. So power is conserved. The incident power should be the sum of the transmitted plus reflected power. So assume zero dissipation of power at the junction. In other words, the power of the incident wave would be equal to the power of the reflected wave plus the power of the transmitted. That's like a hint that's given to in the question. So this question covers all aspects of these kind of things, along with a lot of basics about the equations and all. So just start with the first part, that just from the basic information that you know about a wave, see which type of wave is propagating in which type of medium and how it affects each of the properties of the wave, like frequency, wavelength, etc. And figure out the first part. Then we'll come to the second part, writing the equations. And when we come to writing this equation, we'll see that the reflected wave should be written with the understanding that we have got earlier, that if the reflection is happening from a rigid boundary, then there is phase inversion. If the reflection is happening from a soft boundary, there is no phase inversion. Now here, we will assume that the reflection at the junction is like reflection at a rigid boundary. Why? Because the string on the other side is heavier. So this is because mu2 is greater than mu1. So it is reflecting off a boundary of a heavier medium. So heavier medium means we'll treat it like a rigid boundary. So we'll have to take that into account when we are writing the equations. Okay, so we just start with the basic part first, which is the wavelength, frequency, etc. Okay, so let's quickly understand. So see, for the wave which is traveling, incident wave is on rho 1. So it travels with a speed which is like this, right? So that is 1000 Newton divided by mu, which is mu1, which is given to us as 1 gram per centimeter. So that is 0.1 kg per meter. So kg per meter. So remember this conversion that 1 gram per centimeter is equal to 0.1 kg per meter. So in SI units, it becomes like this. So it becomes 100 meters per second. Frequency is given to us in the problem as 50 hertz. So wavelength will become V1 by F. So 100 by 50 or 2 meters. So it will have an omega of 2 pi F, which is 100 pi radians per second. And K of 2 pi by lambda or pi radians per meter. And a wave speed, which we already discussed, 100 meters per second, and a wavelength. So these are all the properties of the incident wave. This is for the incident. Now, similarly, we'll discuss for the other two waves involved over here. Similarly, for the reflected wave, the reflected wave is also part in which stream? It's in rho 1, but along negative x direction. So the reflected wave will also have the same frequency. So that is 50 hertz. But it will have the direction opposite. Passing to the opposite direction, its V will be V1, the square root of T by mu1, which we saw as 100 meters per second. Therefore, lambda will be V1 by F. That lambda 1 will be 2 meters. So the reflected wave will also have an omega of 100 pi radians per second. The K of pi radians per meter and a wave speed of 100 meters per second. That's the same thing. But the transmitted wave that is on rho 2 along positive x direction. So it will have a frequency same as the incident. So the frequency will be 50 hertz, but it will have a wave speed which is square root of T by mu2. That is square root of 10 raised power 3 newtons divided by 4 into 10 raised power minus 1 kg per meter. So its wave speed is reduced to 50 meters per second. So its wavelength will become 1 meter instead of that one's 2 meters. So this one, the transmitted wave, will have an omega. Once again, the same as the other two, 100 pi. It will have an omega of 100 pi radians per second, but it will have a k which is different. It will be 2 pi by lambda 2. So its k, let's say k prime, is becoming 2 pi radians per meter. So this wavelength is 1. That one wavelength was 2. So this is about the wavelength, and obviously state speed is 50 meters per second. So we got all that. So now as far as the equations are concerned, so that's done with part 1. Now part 2, equations of reflected wave. Remember, it's traveling in the negative x direction. So it will have some amplitude if we don't know, let's say AR, but sine omega t plus kx. And remember that there is a phase inversion because it's a rigid boundary. This is because of phase inversion due to reflection at rigid boundary. The rigid boundary. We discussed why we have to treat the boundary as rigid, because the string on the other side is heavier. So here the reflected thing's equation is not known. I mean amplitude is not known, but omega we saw is 100 pi, and k we saw is pi. So that is the reflected wave. Whereas the transmitted wave, that will have an equation of, let's say, yt, which will be some amplitude which we don't know as of now, but sine, same omega, but different value of t and t is phase. There's no phase inversion for this because it's transmitted. So where this amplitude we don't know, but the omega is the same as the incident and the reflected, 100 pi radians per second. But k prime was different because the medium has become different. So this is this is 2 pi radians per meter. And this one was pi radians per meter. Okay. So these are now my wave equations. So the first two parts, this is how you deal with them. Now the third part, we have to find the amplitudes of the transmitted and reflected waves, and for that, partly we will use the relationship that power should be conserved. So the incident power should be equal to the sum of the reflected power and the transmitted power. Making use of that, we will be able to find the amplitudes. So just make sure you understand this part and the equations first. Okay, so the parameters are clear, I hope. Now you come to the equations. And then finally you will see from the equations how we'll find the two unknown amplitudes. So this is a slightly tricky type of equation in ways to solve. And make sure that you understand everything in a lot of detail over here in the class, because most of the reference books don't have detailed explanation of this kind of thing. One or two books will show you a solved example of this type and show you some numerical values. But the detailed explanation of why the phase constant is pi, or in which case it is 0, which case it is pi, etc. So make sure you understand the detailed explanation of this concept. So you can even reduce this equation now to this. You can reduce it to y reflected is equal to some unknown amplitude into sine of omega t plus kx, but bring the pi outside by making it a minus sign. Use the identity that sine of theta plus pi is minus sine theta. So you can write this effectively as minus of this, using the relation that sine of theta plus pi is minus sine. So I'm guessing you're clear up to this step, these two steps. Then we found everything other than the amplitudes. Now to find the amplitudes, this is the third part. We will, so there are two unknowns. So we need two equations. That means two separate pieces of information or two conceptual things have to be applied over here. And let's see how we do that. So again, make sure you pay close attention for how to find the amplitudes. So to find the transmitted wave's amplitude and the reflected wave's amplitude, given the value of the amplitude of T0, this is given to us incidentally. So we use two things here. First, we use the fact that power conservation because of no dissipation. So that means the power due to the incident wave is equal to the sum of power transmitted to the transmitted wave plus the reflected wave. Now remember, the formula of power was half mu v omega square e square for a transverse wave, or more conveniently we could write this as half square root of p mu omega square e square. So this converts into a very simple equation. The incident wave is in which medium? Rho 1, okay. And all the waves have common frequency, so common omega. So this term omega square will be common everywhere. The transmitted wave is in which medium? The heavier wave, mu 2. And same omega, but amplitude et square. And the reflected wave was back in the same medium as the incident, the lighter one. So this equation actually reduces to a simple term like this. That is, if you just divide the whole thing by square root of mu1, you will see that E0 square is square root of mu2 by mu1 times E transmitted square plus E reflected square. So in this case, mu2 was 4 gram per centimeter. mu1 was 1 gram per centimeter. So this ratio then becomes 2. So the first equation that we get is E0 square is equal to 2 times E transmitted square plus E reflected square. So this is equation 1. Now we are going to require a second equation also to find out the two unknowns. So that will come up to this. Just a minute. Just coming back to this. Alright, so this is my first equation. So first, just make sure you're clear with this. Then we will come to how to generate a second equation. All right, so this is making sense. We're just making use of the formula for power transmitted for transverse wave. So the sum of the powers transmitted by the reflected wave and the transmitted wave should be equal to the power coming into the junction through the incident wave. All right, so this is clear. Now let's come to the second thing, which will give us an equation. So we have to use the fact that the string does not break at the junction x equal to 0. So that means the snapshot picture equation, that means y as a function of xt should be continuous at x equal to 0. So this is a very interesting concept here. So what is happening is you have the lighter string on this side and you have the heavier string on the right hand side of x equal to 0. So at any point of time, the shape of the medium is not like this. The shape of the medium is due to a combination of the waves which are propagating. So here there is some resultant kind of shape like this. And here also there's some kind of resultant kind of shape like this. Whatever this is, whether this is more or less, it doesn't matter. But at this point, there should be continuity. It can't be that the string has broken. So at the junction, we cannot have a situation like this at the junction that, one is like this and the other is like this. So that would involve a break. So that means the value of y at x equal to or x tending to 0 minus should be equal to the value of y at x tending to 0 plus. This is that left hand limit is equal to right hand limit. And they should be true at any instant of time. So that is what we mean by saying that it should be continuous, because there is no break in the function. So that is the concept that we are going after. So now you can see that on the negative side, where the string 1 is operating, on the left hand side of the junction, what is the net displacement? It is the superposition of incident wave and reflected wave. So keep in mind here that for x less than 0, that is on row 1 to the left of the junction, this is by incident plus by reflected. So the incident was E0 sine omega t minus px, and the reflected was E reflected sine omega t plus px plus phi. So this was y as a function of x for all x less than 0. So y at x tending to 0 minus will be the sum of these two things at x tending to 0 but on the negative side. So they will become E0 sine omega t plus E reflected sine omega t plus pi. Because remember, there's a phase inversion. So this is actually now becoming, if you take the pi into account, it's becoming an E naught minus E reflected into sine omega. So showing you that just on the left hand side, the oscillation is happening with an amplitude of E naught minus AR. That's very obvious here that the net amplitude should be E naught minus AR. Why? Because the reflected wave is in phase inversion. So that's an easy way to remember that this result will obviously come as E naught minus AR. Whereas on that side of the string, whereas for x greater than 0, that is on the row 2, that is to the right of the junction, x equal to 0, your y is nothing but y of the transmitted wave. There's no other kind of wave present. So that means the equation for y as a function of xt is simply your transmitted wave equation, which was some this into sine omega t minus e prime x. This is for x greater than 0. For all x greater than 0, the resultant wave equation is this. Whereas for all x less than 0, the resultant wave equation is actually the superposition of these waves. So now you can see you put the limit x tending to 0, but on the positive side on this, and you will get this. So the limit x tending to 0 positive, this should become et sine omega. It's very easy. It's just a single amplitude term of this. Now we have the continuity equation at x equal to 0. So limit x tending to 0 minus should be equal to limit x tending to 0 plus. So we saw on 0 minus, it was just the incident amplitude minus the reflected amplitude into the oscillation term. And on the right hand side, it was just the transmitted amplitude into the same angular frequency. This gives us a very simple second relation that E naught minus ER should be equal to E transmitted. So that's our second. And now solving equation 1 and 2. So equation 1 was that E naught square was equal to what was it? 2 times E transmitted square. So 1 by 2 times. So 2 times plus E reflected square. This was equation 1. So solving 1 and 2, get E transmitted and E reflected. Because E naught was given to us as whatever 2.4 millimeter. It's just a quadratic equation we are solving. So this whole solution is the thing I was telling you about, that reference books will not give you the detailed analysis of this. Okay. Just a couple of numerical problems in DC fund and all, they're directly solved. So might not understand fully what's happening in the solution. So make sure you get this whole thing wrong. So conservation of power is giving us one thing, and the other equation is coming from the fact that the string doesn't have a break at the junction point. So the equation of the resultant wave y as a function of xt should be such that it is continuous at the point x equal to 0. Because if it is discontinuous, that means it's showing a shape such that there's a breakage at the point x equal to 0. If it is not continuous, then that's what it means. We don't want that. It should not be discontinuous. It should be continuous. Yeah, Ashwin, would there be energy change in reflected wave and transmitted one as compared to incident? Yeah, I mean, supposing here what is happening, but the energy change in the sense that the total power of the incident wave is divided in some kind of ratio between the transmitted and the reflected wave. Now, what kind of ratio it divides in, whether it is 40% is to 60% or 20% is to 80% or whatever, that depends on all these factors. It depends on the ratio of mu2 and mu1, and it also depends on whether the reflection is happening at a rigid boundary or a soft boundary. So in our example, it's happening from a soft to a rigid boundary. The transmission is going from the lighter string to the heavier string. So reflection is happening at a rigid boundary. So there is phase inversion. Whereas suppose the incident wave was on the heavier string and it was getting reflected off the lighter string, then it would have been in phase because the boundary would have been the flexible kind of boundary. So that would have given us a different kind of ratio of the powers. Understood now? So the total power of reflected plus transmitted will be equal to power of incident. तो वो power of incident किस ratio में divide हो रहा है between transmitted and reflected? That depends on both the factors, whether there is phase inversion or not, and also on the ratio of mu2 and mu1. And you can see how those factors are affected by this by looking at the final equation 1 and 2. That I've written down below finally. You can analyze from that. Okay, people. So hope the concept is clear over here. So I've given you a couple of questions based on this in the worksheets. So you can try them out. So both the combinations are there. Here, like the incident wave is going from the lighter to the heavier string. There I've given you a question which has that as well as the reverse of that. That the string is incident, the wave is incident on the heavier string and it is bouncing off the junction of the lighter string. So remember, if the junction is with the lighter string on the other side of the incident wave, then you will treat it like a flexible boundary. So the phase constant phi for the incident wave, for the reflected wave will become 0 instead of pi. So that's where that concept becomes important that we discussed earlier. So these are slightly tricky questions specifically for JEE Advanced. So make sure you try them out and not have too much difficulty. However, given that the process of the analysis is lengthy, so typically this doesn't come in JEE mains at all. It's not expected at that level. Now, moving on to the next thing in waves, we'll just understand one very simple formula based on that. So we will begin with, and next time we'll discuss more in detail about the phenomena of interference. Now, this is much easier to understand because partly also because you're familiar with superposition of SHNs. Interference of waves. So this is a phenomena which applies to all waves in general, though here we are discussing it in context of transverse one-dimensional waves. Okay. So interference is, in this case, we are discussing about for transverse one-dimensional waves. So interference happens when waves of identical frequency superimposed. So it happens due to superposition, or that is overlap of waves of identical frequency traveling in the same direction, not in opposite direction, but in the same direction. So not like an incident and a reflected wave, not that type of thing. In the same direction along a string. So the physical situation you can think of where interference happens is something like this. You have that infinitely long string. So don't have to worry about the reflected wave coming back and superimposing. It's going to infinity along the x-axis. But now you have two sources. You have source S1 and S2. So these are simple harmonic oscillators. Okay, but of identical frequency. So identical frequency f, let's say. Okay. So then at a point p like this, which is at x equal to x, let's say, what is the net displacement? That results from the superposition of the waves created by the first source and the second source. So just a second, guys. I'll have to reshare the screen once. Yeah. Okay. So suppose the source S1 creates a wave which is of the equation some amplitude sine omega t minus kx at the point P. That is, if the source S1 was operating on its own individually, it would have created a wave like this, where omega would have been 2 pi f, okay, k would have been 2 pi by lambda, okay, and v is equal to f lambda or square root t by mu, where t and mu are the properties of the state. So given the frequency of the source and the properties of the medium, we can find the wave equation in terms of the amplitude. But similarly, suppose S2 creates a wave which is y2 equal to a2 sine omega t minus kx, because it has the same frequency, is passing through the same medium, so it will have the same wave speed. So obviously k will also become the same, but there might be a phase difference involved. So that phase difference we call delta phi, where delta phi is the phase difference between waves y1 and y2. Okay. Now that phase difference may be because of different path lengths. Okay. This is because of different path lengths. That is, S1p is not equal to S2p. The distance from S1 to the point P is not equal to the distance from S2 to the general point P. Okay. Or time difference, because S1 and S2 may not be synchronized as sources. They might not be in sync. They are having same frequency, but they're not necessarily in sync. So these combination of reasons can create a phase difference delta phi. Okay. So that quantity delta phi is called the phase difference. Then with S1 and S2 both operating together, okay, the net displacement at the point x as a function of time becomes superposition of y1 and y2. But which type of y1 and y2? Two wave equations which are having same frequency and traveling in the same direction. So whenever we are adding two wave equations such that the two waves concerned are having identical frequency and are traveling in the same direction, the phenomena is called interference. Okay. So this becomes our net distance. Now from here, how we proceed is just a matter of trigonometry. So because omega t minus kx is a function of time, so we take it as time and x. So let omega t minus kx is theta, because it's variable. Okay. Delta phi, remember, is here a constant. It's not changing with time. Okay. So we can write y net as e1 sine theta plus e2 sine theta plus delta phi. Okay. So then you proceed like we used to do in trigonometry, or how you did in superposition of SHMs. So you just expand this term using the sine A plus B formula. So you can write this as E1 sine theta plus E2 sine theta cos delta phi plus E2 cos theta sine delta. Now when you're solving this equation that we got by expanding, remember that theta is the thing which is variable. It's varying with x and t, whereas delta phi is a constant. So we want to solve everything in terms of theta. So first take sine theta term common. So you'll see you get E1 plus E2 cos delta phi, which is all a constant. This whole term is a constant, into sine theta, where theta is the variable. Okay. Plus take the cos theta term separately. So E2 sine delta phi. Now this is a constant, and this multiplied by cos theta. So this whole constant, let's treat it as alpha, and this whole constant, let's treat it as beta. So this becomes alpha sine theta plus beta cos theta, which you can now use that trigonometric trick, multiply divide by square root of alpha square plus beta square. Because remember, alpha and beta are constants. So you can easily do this. And then take the root 1 upon root alpha plus beta square inside. So you can treat this as square root of alpha square plus beta square into this thing. Some, let's say, sine theta cos epsilon, let's say, plus cos theta sine epsilon, where cos epsilon, as you can see, will become alpha upon root of alpha square plus beta square, and sine epsilon will become beta upon. So then expand this further, and since alpha and beta are constants, so this root of alpha square plus beta square is just a constant, so that is the net amplitude into this will become sine theta plus epsilon. Now let's recall that theta was nothing but omega t minus kx, plus we have this term. So the resultant wave equation, which is coming from the superposition of those two, is becoming like this, okay, where now E net is a constant. It is the net amplitude, which is obviously a constant, and that depends on the individual amplitudes A1, A2, and the phase difference delta phi. And we'll just substitute in terms of alpha, beta, and all, and we'll see next what it is. And similarly, epsilon is also a constant. Okay. And this constant depends on, again, these three terms, A1, A2, and the phase difference delta phi. Okay. So this should be like a repeat of what we've learned in superposition of SHMs. Only there was only omega t term inside the bracket. Here it is kx minus omega t or omega t minus kx. That kind of thing. So just understand this whole part. We just take a couple of more minutes and finish the solving thing at the end. So you might remember in SHMs, the amplitudes are added according to a phasor diagram. The same thing will happen here also. Okay? But only instead of adding to SHMs, we are adding to wave equations. the page a little up in the sense that touch. You want to note down this part. Is it all right now, Ashwin? Okay. So this solution now we want to do fully by using the trigonometry method. So first just make sure. Okay, so finally when you're solving this, you make use of this trigonometry trick. How we generally solve alpha sine theta plus beta cos theta. It becomes root of alpha square plus beta square into sine of theta plus something. So that okay, so this is a standard trigonometric method. So once you reach here, now you can see that also the formula of the net amplitude. So in this, the net amplitude will come like this. Square root of that alpha square plus beta square, where we had substituted alpha in place of E1 plus into cos delta phi, and we had substituted beta in place of E2 sine delta phi. So square and add these two. So your cos square plus sine square is 1. So you get this very familiar kind of formula. This is almost like the addition of two vectors. But only here it is the addition of two amplitudes according to their phase difference, delta phi. Delta phi is not really an angle between two vectors here. This becomes a formula for the net amplitude, and so this can also be, this formula can be also remembered by a phasor diagram of the sun, where you represent the individual amplitudes E1 and E2 by two arrows, just like you represent vectors by arrows. But now you represent amplitudes by arrows, so not vectors, but amplitudes by arrows, such that the angle between the two arrows you've drawn is actually the phase difference, delta phi. And the resultant amplitude now becomes this third side of the triangle. The net amplitude coming from the interference of these two is this. Okay, so this is the derivation of the formula of interference, and also from this you can see that net amplitude has a maximum value of A1 plus A2 and a minimum value of the difference of A1 minus A2. Okay. So this maxima is for the phase difference being an even multiple of pi, and this minima is for delta phi being the odd multiple of pi. Whereas for any other delta phi, it is in between these two values. So as I said, this is the simpler part of waves, the superposition and interference part. Because once you get familiar with the formula, the questions are mostly formula based. Directly apply this formula. E1, A2 and delta phi will be given in the question, or you can work it out from the language of the question. And then all you have to do is the phasor addition. This kind of phasor diagram method is called the phasor addition. You're familiar with the formula from vectors. Alright people, so hope this is clear. So with this now we conclude today's lecture, and we've concluded most of the part of transverse vibrations of a string. Next lecture we will see some applications of interference, some examples, and we will see the last part, which is standing waves, or string, the waves which are created when a string is bound between two rigid points, and we have what we call the harmonic modes of vibration, or standing waves or stationary waves created. And with that we will finish the transverse waves. One lecture or more it will take for me to discuss all the questions related to transverse waves, and then we will move on to sound, which is the second chapter of mechanical waves. Okay. So by next lecture also try to complete the pending questions in the DPP worksheets which I had given. Plus, if anything is remaining in the original HC Verma set, which I had set up to question 28, you can add some questions to that. I will send you some question numbers. You can work out. So keep those doubts ready in the next lecture so that we can start with the discussion of that. All right. That's it for today, people. Thanks for attending.